And start. All right. Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk, unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. So please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now, let me introduce our speaker today. It is an honor, a great honor, to host Michael Brenner, who is the Michael Cronin Professor of Applied Mathematics and Professor of Physics at Harvard University, where he has taught and done research since 2001. He's also a principal scientist at Google Research, where he works at the borderline of AI and science. Today, Michael will talk about scientific uses of automatic differentiation, which is an exciting topic. Please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton to Michael by asking one random question as usual. Today's random question is, what is one goal you have for the near future? And answer that question and then...
And then I'm allowed to talk. I see. So, okay.
Yes.
So the goal for the near future would be to accomplish something. This talk is, you know, there's lots of potential, but I would really like to turn it into something, you know.
Something concrete.
Yeah. Something that's not a model problem. That would be my goal.
Oh, the real problem. We have a lot of real problems.
You guys have a lot of real problems. That's right.
Yeah.
You know, a real problem where the answer actually matters.
Awesome,
you know,
awesome.
So that maybe, I don't know. So maybe you guys can help. This is my actual goal. So,
awesome. Okay. A lot of
and the
chances
sooner
of
we can do it, the
collaboration.
better we are, right?
Sooner is, yeah, awesome.
Yeah.
Okay, the stage is yours, Michael.
Yeah. Okay. Thanks, everybody. So thanks for having me. So I should admit up front that this talk has too many slides in it, and but what I want to try to do today is just give a broad idea, which I'm sure will not be new to many of you, but I just to sort of tell you, to sort of explain the way that we've been thinking about these problems, and then I'll dive into some examples, and I'm going to try to spend most of my time on one of the topics that's in this set of slides, which is on using automatic differentiation to learn algorithms for PDEs, which I think is probably more synergistic with things that are happening there. But if there are other interests that people have, I'm happy to modify. I don't have to get through this in any way. So, okay, so the preamble goes like this. So many of us have been inspired by advances in machine learning, which gives rise to, you know, lots of interesting mathematical questions. I mean, like, you know, why do large, you know, neural network machine learning models work so well? Why is overparameterizing useful, et cetera, et cetera? So I think this is a fascinating field, but that's not what I'm focused on. So what I'm, and actually this is just an example actually that I was, last week I was in Santa Barbara, and I just for fun, I was just, you know, stable diffusion, you know, a crocodile surfing on a hamburger in Santa Barbara, and you stick it into this thing and out comes pictures. And I guess I would have said, I mean, you know, a couple of years ago, I think any of us would have said that a function that is able to give, you know, a distribution of answers like this is essentially impossible. And now, you know, now they exist. So, okay, but I'm not interested in that. I mean, actually, I think that's very interesting, but I'm not interested in that. So the question that I want to ask is, and the main question I'm interested in is whether or not the tools and ideas that made things like that possible also give us new ways of attacking really core unsolved science problems or physics problems of the sort that we would have done ordinarily 5 or 10 years ago. So that's what I want to know the answer to. And that's what we've really been focusing our research program on, both actually at Harvard and at Google. And so to that end, I mean, I think that, you know, there's a lot that people have been taking from the machine learning community. I mean, there's lots of physics papers that include neural networks in them in various ways. So I sort of care much less about that. I think that that to me, there are really two lessons that we can learn from the machine learning community as a community of scientists. You know, the first is really the existence and the use of excellent software frameworks, which include within them native automatic differentiation, which will be what I will talk mainly about today. This basically makes it possible to solve optimization problems that, you know, 20 years ago were just impossible. I mean, I, like probably many of you, you know, I've spent part of my life writing adjoint codes trying to solve optimization problems, and and I mean, I don't know if this will resonate with any of you, but to me, like, I remember, and maybe this dates me. When MATLAB first became, when I first started using MATLAB, I used to write all of my matrix inverters myself, basically. And, I spent like, a good number of years writing sparse matrix inverters to solve science problems of the sort that I wanted to. And then at some point, I sort of started to appreciate backslash as a technology, which essentially saved my life. I basically had to stop doing that and I could start like solving problems. And I feel very much the same way with these native automatic differentiation frameworks. It's like, there are lots of optimization problems that I would love to solve. And I think that there are a lot that are relevant for science problems all over the map. And that normally, up until recently, we wouldn't have even asked the questions that I'm going to ask in this talk. We could have. The questions existed. It's just that the possibility of answering them wasn't there. So that's sort of one thing that I think the machine learning community has made possible. And the reason that there's been such or at least one of the reasons there's been such rapid progress on things like diffusion models for image generation is because the software frameworks are great. They make it possible to iterate ideas very, very quickly, and for a community to iterate ideas and to make progress. So the other thing which is important, and this I'm going to touch on less today, but I just wanted to say up front because I would be curious your all's perspective on this. Because you guys kind of like, I would love to solve a complicated problem and believe the answer, and you guys sort of do this all the time. And I think that one thing which is hard, especially when solving optimization problems of the sort that I'm going to describe today, is that if I take a set of equations, PDEs, ODEs, whatever, some mathematical model of a phenomena, then of course we can pose and solve optimization problems on the solutions of those equations. But the question of whether or not we believe the model enough so that the optimal solution actually has any relevance whatsoever is really open. And in many situations, our models just aren't good enough to basically do this sort of thing. And I think one of the things that's impressed me about the machine learning community is just how careful they've been at setting up benchmarks to measure accuracy for important problems, and to always measure against the same benchmarks, so that when 10 different groups work on a thing, they can all compare, and it's routinely compared solutions to each other, which has the advantage that one can then iteratively improve things. And I wish this were true of models in the physical sciences. So I'm not going to talk about this very much today, but I just want to put this out there in case anyone has any interest in discussing, is that I just feel that like a lot of the modeling that the communities that I'm aware of in the physical sciences have done over the years, has the feature that it's really great, but it doesn't build on itself in the same way that the ML community has done. And I think that there's really a lot that we can learn from that. And just as an example, this stable diffusion thing, as some of you probably know, it's really very new. It just came out, and like you can go, like, this is summer 2022, and like you can go right now, and there are open source software frameworks, Hugging Face, basically. They're just beautifully written, like they're clearly explained. It doesn't require on one hand, and then on the other hand, benchmarks. Like they're always, this is benchmark is from a month ago of basically a large multimodal data set that's made to be open sourced. And the importance of this is that it means that if anyone wants to compete against tasks which lead to models like this, then there is a clean benchmark that you have to beat, or at least you can compete on to do this. And I wish this were true. I don't know, like, to invent a problem. I wish this were true for modeling the dynamics of a protein, or for modeling some complicated heat transfer problem. And and maybe I'm ignorant, and I would love to be taught otherwise, because I think, again, you guys are, Livermore is one of the places in the world that I see of as being like really the brain trust for this kind of thing. So if maybe this exists and I just haven't noticed, but to me, it's like everybody has their own model, and there isn't really this sort of culture. And I feel like it's really slowed us down, actually, and that if we could figure out a way around it, it could really help. Anyway, okay, so that's those are my things. So, and as I said before, our thesis is, and really the research program I'm going to describe to you about, is that we think that these lessons, if we could apply them in hard science problems, we can make a lot of progress. And that's because, for one thing, and this will be something I will touch on a lot today, is that there are lots of non-convex optimization problems that I at least would have never had the courage to tackle or even formulate until recently. And now it's something that, we can just try a different one every day and try it in different ways. And it's really exciting. And I just want to, just as a meta idea, I'm going to spend most of the time on PDEs, but I sort of want to mention this as a motivation for my own research group, for things that we've been thinking about. And if this resonates, then I'm happy to discuss as well. Is that one of the things we've been interested in my research group at Harvard over the last couple of years is what we call synthetic living materials. And the idea is that, like, if you look at biology and you look at the phenomena that exist for materials in biology, they the materials are made out of parts which have to be programmed, both in terms of the way they interact and the way that energy is fed to them. And when they do that, then there are all of these kind of remarkable things that happen, microtubule assembly and disassembly, DNA proofreading, the assembly and disassembly of Clathrin cages. And these are things that actually in synthetic materials, like we just don't know how to build materials that are able to have this type of functionality. And so a question that we've been struggling with for some time is like, how can we as a computational or theoretical group come up with ways of making design choices for experimental implementations of materials to enable functionality that emulates this? And at the core of it, there are really two issues. Like one is, can one write down models that we believe enough that we actually care about, an effort to optimize them to make an artificial microtubule? Like a graduate student this morning was showing me her model of an artificial microtubule, which is really quite fun. But it's not, it's sort of, it's practical enough that you could imagine implementing it, but yet implementing it is still a problem. That's on one hand. Then on the other hand is, can you find ways of optimizing the large parameter spaces that exist to basically enable functionality? And I think that this is just an example of the types of non-convex optimization problems that we don't ordinarily solve. And this has driven, a lot of our work in the last couple of years. And one of the reasons I've gotten excited about automatic differentiation as a technology is because I think it gives us a new way of really addressing both aspects of this, which I may or may not touch on in this talk, but these are just the big ideas of what I want to say. So benchmarks, I already said this about benchmarks. Have we given up on accurately model? Actually, this would be a wonderful discussion with all of you. I wonder, we have models, we accept the errors. I mean, maybe we should be like the machine learning people and really nail down them. But anyway, I don't want to. So okay, so with that said, then this is my outline, and this is far too much material to cover. But maybe this will give you a flavor for the sorts of problems that we've been working on, so that if any of you are interested, if you just send me an email, then we can set up time to talk. If it's synergistic with things that are going on at the lab, I would love to discuss it. But I'm going to spend most of my time on the third topic, which is discovering numerical algorithms for PDEs, because this is in some ways the most developed of the areas in our own work, but is and I know overlaps things happening with you guys. But I mean, just to sort of give you other things that we've been working on is designing energy landscapes for self-assembly. So this involves considering materials where one can simulate or formulate the ways that they interact, and then trying to figure out if we can program them, either kinetically, in equilibrium self-assembly or non-equilibrium or whatever. So the design of non-equilibrium processes is a topic of great interest. For example, one of the things that we've been doing, and I will just say this as an introduction, and I probably won't discuss it just for lack of time, is that there's the wonderful work by Dzerzhinsky and Crooks on non-equilibrium thermodynamics, on forming, looking for, formulating optimization problems for minimizing dissipative work and trying to find out how to optimize near equilibrium processes. And the challenge of that work is that, it's absolutely gorgeous and beautiful, and but the challenge is that if you push it much further out of equilibrium than just linear response, then the calculations become very challenging to carry out analytically, which is the way that they tend to be carried out. And so one of the things we've been doing is using automatic differentiation to just calculate to do exactly what they're doing, but to do it at wherever you want, basically. It just doesn't matter. It ends up being, like 20 lines of code or something. And I think that this is exciting because it just means that the sort of intellectual framework that they've set up could be applied more broadly. I'll touch on this. So other things that we've been thinking about, and again, I won't talk about them really, but I'm mentioning them so people know what we're thinking about is, I've gotten very interested with a visitor right now at Harvard in designing rheology. The question of, if you consider like multi-particle rheology, could you tune the distribution of particle sizes and interactions to achieve rheological outcomes, even nonlinear rheological outcomes? And this is something which, and so these are hard computational problems, and it's a hard optimization problem, but these are things that we're starting to take on. So another set of problems which I think is very interesting is programming cells for cell division decision rules for tissue development, and then our model's good enough. So okay, so that's my list of topics. I don't know, you guys, if anyone has questions or wants to interrupt, then I really welcome comments. I know that I'm very conscious that I very rarely make sense, and so I'll just keep going. Do you have something? Are you just put
No.
that's thumbs up? Okay, so automatic differentiation. I think I'm going to assume that you all know what automatic differentiation is, if that's okay. I'm not going to. So I mean, automatic differentiation is essentially a process in which one, as opposed to numerical differentiation or symbolic differentiation, what we do with Mathematica or SymPy or just doing numerical analysis, in which one takes a function, unrolls the computation graph of the function, and then compiles the function in such a way that using the chain rule we know the both forward and backward derivatives of the function exactly. And this is an idea that is old, but that recent machine learning software has really made much more prevalent in open source in open source libraries. And the idea is, I mean, like, I guess I sort of at some point in my youth, as I'm sure with many of you, I fell in love with the adjoint method as a way of optimizing for solutions of differential equations, which of course one implements by simply considering, if you have a set of differential equations dx dt equals f of x, then what you do is if you want to optimize some loss function, let's say the loss function is just some function of x of t, then what you do is you add a constraint that states that the differential equations are satisfied for x of t. And by doing this, it essentially means that you have to solve for the prices, is that you end up with an optimization problem where you have to solve both the forward problem for x of t, and you have to solve, it turns out, a backwards problem for the adjoint lambda of t. But in so doing this, you end up being able to compute derivatives of design variables in such a way that it doesn't depend on the number of design variables or of control variables. And this is very important, because if you're if you're designing materials which have many free parameters, you don't want to have to do a forward solve every time you want to take a derivative. And this basically makes it possible to have algorithms that scale. So I sort of spent part of my youth, or even not youth, coding these things. Like, if you want to solve something, you code the adjoint problem. And as some of you might know who've done this, it can take a lot of work to basically code the adjoint problem to be able to do this. And the amazing thing about these automatic differentiation frameworks, at least to me, is that it just works automatically as long as you follow software rules. So let me just give one example of this, which, again, I assume that you all know this better than I do, but in case you don't, this is just a plug of something. So this is a package which is called AutoGrad, that was written by Ryan Adams and his group. Ryan is now at Princeton, but he used to be my colleague at Harvard. And he wrote it actually because it was in the early days they were inventing graph neural networks to study molecule property prediction. And, you had to take the derivatives of graphs. And at the time, this was more than a decade ago, when, all of these packages didn't exist and they needed to write the code, and they decided they would just write, essentially a wrapper of NumPy, which is what AutoGrad was, that basically, embedded automatic differentiation into the solver. And if you go to their website, which still exists, the GitHub site, then, they have this example, which I like very much, which is basically to find the initial conditions of a velocity field of a flow, so that when you advect the die, which starts out, in this banded structure, that it ends up being a peace sign, basically. And it can be anything you want. You can put in any image. And the thing that I guess I just find amazing is that this is the code that basically solves this problem. And so there's a simulate function, which, there's an advection projection. There's some scheme for basically solving the smoke. So smoke is advective of time. So this simulates the smoke. And then here's the objective function. So you take the the initial coordinates, the x and the y, you simulate them. So final smoke is simulate of the initial x, vx, and vy, which is what you're going to optimize over, the initial distribution of the smoke, which are those bands, and then some number of time steps. And then the objective function returns the distance from the target image of the final smoke. So this is just like an L2 loss of the peace sign and whatever the solver got to. And then, with an AutoGrad, you just simply compute the new function, which is value in grad of objective, and it automatically returns for you the derivative of the objective function with respect to its parameters. The parameters are the initial velocities, and then you can just write a simple gradient descent algorithm to find the answer. And I guess this is not rocket science. I mean, maybe actually this is rocket science, actually, but this is not complicated. I mean, this is something we could have written this code whenever, any number of years ago. But the point is, and this is the thing that I'm just so struck by, is that it couldn't be done so easily. And the reason why it's important that it can be done easily is because it makes it possible to experiment very quickly with lots and lots of variants of things, which is, I think, important, basically, in the physical sciences. So this is what's impressed me so much. And actually, so AutoGrad basically, as I said, it was originally written at Harvard, and it's actually the antecedent to JAX. So there are a bunch of packages for automatic differentiation that have come out over the years. But JAX basically is just in time, am I going to get it right? AutoGrad and XLA. So AutoGrad is the middle part. So the group that basically is at Google, responsible for JAX started out, a core part of the group started out in Ryan's group at Harvard. And because of the technological importance of this, then there's just tons of open source tools that one can use to sort of make this even better. And this is just an example of a function which I just find amazing. This sort of automatically parallelizes, across GPUs such calculations when you're rolling out. And when you're rolling out simulations or things like we do, then it's just really helpful to have professionally written things. So so my other meta comment before I talk about something substantive is that of course this was mainly developed for machine learning. This was really about machine learning technology, but the point is that architecturally dynamical systems of whatever sort you want and a machine learning model really have a lot in common with each other. I mean, that is, at least in terms of computing gradients of things, like it's they're both rolling out, especially if you roll out a dynamical system that's like pushing data through a neural network of whatever architecture. And I mean, there are differences in this that I'm not claiming that these problems are like these problems. Indeed, I think there's been a lot of effort in the community on what it takes to solve non-convex optimization problems in traditional machine learning, and there's been much less effort in dynamical systems. And I think one of the things that we as community has to do is to learn all of the tricks basically that are required to basically really solve problems in this space well. But I think that's what I find exciting. So and so let me see. Okay, so that's my introduction. I don't know, does anybody have anything to say? Or should I just plunge forth? I'm going to punch forth. Okay, so what I'm going to do, this is really terrible. You're going to see how badly I designed this talk. I'm embarrassed, but I think that this is probably the right thing to do, is I'm going to just push through these two. I'm going to just flip through the slides for number 1 and number 2, and we're going to talk about PDEs. And then if anyone wants to talk about any of the other things, we can come back at the end, but I would rather make sure I uncover something, do a good job at one thing instead of quickly going through a bunch of things. So let's see. So sorry, and this is like non-equilibrium processes. Non-equilibrium processes. Non-equilibrium processes. Okay, so PDEs. So of course the classical numerical algorithms that we all know and love for PDEs were developed a long time ago, and the traditional algorithm. I mean, you all know better than I do, so I apologize for. But basically, we take the PDE, whatever it is, and we discretize it, and we then turn it into an update rule where we predict the state of the system for the degree of freedom I, which could be a mesh point, or it could be some spectral basis thingy, or whatever you want, at time n+1 as a function of the earlier time steps. And if you take this update rule, then what we do, of course, numerically, is we roll out this update rule, giving the dynamics. And as you all know, there's a tremendous literature in the derivation and the implementation of update rules. But traditionally, these update rules are learned by are things that we derive basically. But nonetheless, and I mean, I think this is just the reality. Which again, if anyone disagrees with this, I welcome. Please disagree. I mean, we've made a tremendous amount of progress. I mean, I think you guys. I mean, the work that you all do is stunning. How much we can simulate in the modern day. But still, we still can't afford even today to simulate very simple situations. And I think this is true of any. I mean, this is just turbulent flow is sort of emblematic of the problem, but it's not obviously the only problem. I mean, if you simply count the number of Kolmogorov eddies in a box of size L, then the number of eddies scales like the Reynolds number to the 9/4 power. And what that means is that if you say, and I know that this is an overstatement, but if you say that every eddy needs 1,000 grid points to resolve it, it's say 10 cubed, then you end up with a formula for the total number of grid points you need, which is 1,000, maybe you would argue it was 100, but whatever, times Reynolds number to the 9/4. And if you start putting in Reynolds numbers of reasonable situations, you just run out of memory very quickly. And this is something like, it wasn't possible, when von Neumann and people like that started thinking about it, and it basically will never be possible to simulate these things. And I think that this is, we shouldn't forget what a problem this is. I mean, it's something that we're obviously all working to fix, but but it's a fundamental problem in our view that that these equations are fundamental, basically. And so an example, of this is that if you consider a weather model, so this is the typical numerical resolution in a weather model. And this resolution, it's not bad. You can see the hurricane, but on the other hand, there's a lot of microscopic processes that are happening inside of each of these boxes. And the fact that we're not resolving them means that there are errors. And what the nature of the errors are, of course, is what, many of us work on, but it's not a pretty situation. So that's on one hand. So now on the other hand, imagine the following, and this is, a Gedanken experiment in a way. Imagine I told you that these curves were solutions to some PDE, and I didn't tell you what PDE they were. And I asked you to solve them numerically. So what you would do, according to traditional schemes, is you would choose some number of grid points, and you will notice that here, just for illustration's sake, I've chosen too few because I'm only having one grid point at the shock, basically, which obviously is not what we want to do. We then take the solution away. We then need to use the differential equations, we need to compute the derivatives of the function at every one of these points. And so what we were all taught when we were young, is that what we should do is we should interpolate this somehow. And so, I don't know, suppose you were trained badly, you would use some sort of polynomial interpolation. And then, of course, there's the well-known phenomenon that is illustrated here, where it gives the wrong answers, basically, and it's precisely because the grid is under-resolved, and the derivative of this function at this point is not what it should be, because we're interpolating with functions that basically underfit the data. So, on the other hand, suppose that I told you something different. I basically gave you the points, and I said, listen, I'm not interested in building solvers that work for any equation. It turns out, just as a Gedanken experiment, the only equation I care about is Berger's equation. And actually, these curves were solutions of Berger's equation. And moreover, here is a large library of solutions of Berger's equations that I put together that you can use when you're trying to compute derivatives. So if you're given the problem in this way, then it shouldn't be a problem anymore. You can basically look at this point. You're not going to overfit like this. There's no overshoots in these solutions. You're going to sort of fit this with a hyperbolic tangent or something, which actually turns out to be the answer, right? And try to estimate the derivative that way, and you will do much better. And so that is to say that there's another view of solvers, which is that instead of deriving the equations from first principles, that we can imagine solving the equations at high resolution, learning what happens when we under-resolve, and then using those learnings to try to feed into the update rule for the solver. And this is essentially what we set out to do. And this is an example of something that with automatic differentiation is actually not so hard to do. Without, it would be a nightmare. And so let me just sort of show you how this works. So the method basically goes like this. We perform many high resolution simulations of small pieces of a solution. We then train an algorithm to find an update rule to match the average of the high resolution solution on a coarser grid. So that's the way that the algorithm goes. Now this is, I just stated it in words. It's you can easily turn the words into an optimization problem. And in order to solve it, though, you have to be able to do something which is like the smoke thing that I showed you at the beginning, is that we're now not tuning over initial conditions. We're going to be tuning over the parameters in the update rule, trying to match basically high resolution parts of the solution. And the question is this useful and does this work? So, okay, so let me just explain what I mean by averaging. So this is an example of advection of a scalar by a sort of chaotic flow. This is a high resolution solution. This is an exact coarse graining of the high resolution solution. So what this did is we simply just took little boxes of this size and averaged the solution. So what the question is, there are two questions, is given the exact solution, here's the coarse grain solution, could you invent a time stepping algorithm that basically gives you this? So that the way that this was produced was that we took the high resolution solution and we averaged. That's the question, is that does such an algorithm exist even for large degrees of coarse graining? And so that's the question that we kind of went after. And I guess what I wanted to say is that you all know this. Classical numerical analysis, if you take a class, is that typically doing this simply using the laws of calculus that we were taught when we were young to derive the algorithms doesn't work at doing this. If that's how you design the algorithm, it doesn't work, because basically there are either instabilities that occur. This is like with a typical finite volume method, which is pushed on a coarser grid, or you can use a fancy flux limiter or something which is better at maintaining stability, but it has too much diffusion and it smears the thing out. And so the question again that we wanted to ask was whether or not this could be sorted out. And so to do this, we invented the following algorithm. And let me just show it to you in terms of this training procedure. So basically what we did was, I want you to focus on this box. So normally, you know there's some number of points where you know the velocity field where you're trying to compute the derivative, and you might use some interpolation method to compute the derivative. So what we did is we pretended that these interpolation coefficients, C and M, K, are coefficients that are learned basically by the solver. And so we're not going to derive these from calculus, although when we did what I'm about to show you, we imposed constraints on them that they agree with, accuracy constraints at some level, but we allowed them to get learned. We then took these derivatives, we computed fluxes, we then wrote down a traditional time stepping scheme, a simple finite volume time stepping scheme. And so of course, if you wanted to just roll this out, then what you would do is you would just go around this loop, and that's the update rule. But you can also train it, because what you can do is you can go through this and then you can compute a loss. And the loss is going to be, it's going to depend on these coefficients, C sub k, but these coefficients C sub k are really parameterized by the weights of the neural network. And what we're going to do is ask whether an algorithm exists that does what I just said. And this is something which, if you have an auto diff code, then you can easily run. And so, okay, so I'm going to show you this first on, the first thing we did, and this is the sort of simplest thing to try, is to try this on Berger's equation. So this is a paper that was published a couple of years ago. And just to sort of show you how this works, this is a solution to Berger's equation, this black, the dashed curve actually. The black is the numerical discretization. And what these are showing you, these are stencils for the first derivatives for of the scheme that is learned. And these change as you go across the solution. So if you're in this part, which is kind of the smooth part of the solution, it reverts back to what you would have derived because of the way that we've set this up. But when you're in the steep part, it does something completely different, basically. It's just a different scheme that the model has learned. And so then when you time step, it's just learned schemes to basically infect the shock, basically. And so we did this, and this is just sort of showing you an example. This is a chimera graph. So this has X on this axis, T on this axis. So this is unrolling a solution to Berger's equation. This is a unrolling, this is rolling it out on a mesh spacing that's 32 times bigger than the mesh spacing where the data was generated. And we trained on a domain of size 2 pi. So this was the size of a training domain. And then what we did is we rolled out on this entire thing. And then you can ask, how accurate is it? So like, is this accurately rolling out Berger's equation? This thing would have destabilized if you had used a classical method. And basically, if you plot mean absolute error as a function of resample factor is how many grid points are you skipping? I was showing you the 32 one. If you compare basically our method, which is these solid blocks, to other classical methods, then we outperform all of them. And interestingly enough, so the we know method is the sort of best, at least to my knowledge, although there may be people in the room who know much better, the best known method, which was of course a method that was invented maybe 20 years ago, and that is very sophisticated in terms of its derivation. So just for kicks, we asked the model if it could learn a single scheme, right? That you're not changing at every point of the solution, but a single scheme that could be applied everywhere. And we demanded that it had that, and the model, because you can ask it to do that, and it essentially reproduced the accuracy of the we know scheme, which is kind of fun. So this thing basically works. So that was that. And we then, and I'm using it in this paper, which was published a couple of years ago, we tried it on a bunch of other canonical 1D PDEs and said, like, maybe this is not a stupid idea. Now, of course, as you all know, it's, if you come up with an idea, then testing it on 1D problems is the right thing to do, but that's not, I mean, the world is not one-dimensional. So okay, so then so a year ago, we published this paper, which was with the group at Google, basically. So I want to, Stefan Hoyer, Dima Koshkov, Jamie Smith. Aya is actually now a graduate student at Stanford. She was an AI resident at Google for a while, in which we basically took this idea and tried to apply it to computational fluid dynamics. And let me just sort of show you what it is. And this is, again, a model. This is a simple problem in computational fluid mechanics, but this is trying to get at the thing. So okay, so for this, what we're going to do is now we're going to take the full, oh, good, there's a question. I can't, I'm not sure if what's the input?
I can first say, okay, so Qui asked, what's the input of the neural network to get those scheme coefficients?
Yeah, so, okay, so the input, so let me just go back to this. So let me just go back to this picture. I'm sorry, I'm going quickly. So the input are the velocity field on the coarse mesh within some vicinity of the point where you want to compute the time derivative. So it's just like a classical scheme, right? Some number of points, the higher order method around those number of points. But if the points are not close together, then there are the well-known problems. But we feed those points at the mesh spacing into the neural network, which is what computes the seek sub k. And there's some, domain of dependence that one assumes. So it's just like you always do. It's just that now these coefficients are nonlinear functions of the u's that you have to learn. So I'll talk about this a little more when we do the turbulence case. I think the turbulence case is much more interesting, obviously, because it is much more relevant. So okay, so thanks for the question. So turbulence. So again, so what we seek is we want to solve the Navier-Stokes equations. We seek an update rule, and just for kicks. And again, we want to seek an update rule such that the coarse grid matches the fine grid, but it reduce and also actually this I didn't emphasize before. What we really want is for this to work at reduced computational cost, because one thing I didn't emphasize in what I just showed you is that, of course, if you're putting the mesh points through a neural network, you have to pay for that at every mesh point. And if it ends up costing you more than it would have cost you to run the initial high resolution simulation, you're just wasting your time, basically. So I'm now going to be much more careful about this in this part of the talk, and we'll talk about computational cost. So we're looking for an update rule, and this is really a different type of solver, to my knowledge, than those that have. This is like a DNS solver, but it's a DNS solver for which the resolution is much lower than it normally has to be. And actually, the other thing I want to emphasize, though, because I do want to stay, getting back to 20,000 feet just to make the meta point, is that, the beauty of this is that this is a particular goal that we chose to go after, which I think is a natural goal, but you could do whatever you want with this technology. There are lots of things you could choose instead of this. And I think this is one of the reasons I'm so excited about this as an area, is that I just feel like, creativity, it's like if you don't have to write your own matrix inverters anymore. So traditionally, is to consider something which comes sort of an average over the nonlinear. So there isn't the goal of getting pointwise agreement averages. Instead, one tries to introduce a correction to the update rule that basically the statistics. And so, in LES papers 110, things like extraordinarily useful practically. I want to emphasize that what we're doing here, it's like an LES method. But we're demanding more usually, and which is just useful.
Hey, Michael. I guess it's not only me. I thought it was only me, but Michael, your internet seems to be unstable. Can you hear me? Hi, Michael. Oh, that's unfortunate. Actually, let me try to stop my video. Maybe that helps. Hi, Michael. Ooh.
Which is just a word. But this is another thing you could do. So
Hi, Michael.
Yes.
Can you hear me?
Yes, please.
Yeah, we kind of lost you about I don't know, 1 or 2 minutes. Past
Oh,
2
you
minutes.
lost me 2 minutes. Oh,
Yeah,
that's bad. What happened?
I don't know. Maybe your internet connection was unstable.
Oh, okay.
So maybe you can go back
Oh,
a little bit.
okay. I'm really sorry. That's bad.
Maybe you
Where?
can turn off the camera.
Oh, okay. I'm sorry. Where? How do I turn off the camera? How did that happen?
There's a start video and a button
Yeah,
at the
let me see.
bottom, or since you are sharing the screen
Yeah, let me see if I can.
on the yeah.
Sorry. How do I do this? Video. Got it.
Yeah,
Okay.
exactly. Hopefully that makes it
Okay.
the
Sorry. Where should
connection
I start?
stable.
I apologize for that. Thank you for telling me. Where
Yeah,
did?
so if yeah, this slide, if you can start over this slide,
Okay,
yeah.
sorry everybody, I apologize. Something always goes wrong. So please, if that happens again, say I had no idea.
Yeah.
Okay, so traditional LS models are different than the type of model that I described, because what you do is change the update rule by adding an effective viscosity term or something to it, for which you emulate the statistics of the actual solution, even if you're solving on a coarser grid. And the difference between this and the scheme that we're exploring is that our scheme is trying to get on average pointwise accuracy. I'm not making an argument that one is better than the other. I think they're different. And I think what's interesting here is just the ability to go after the type of scheme that we're going as an example, of which, as I said before, there are many other things one could imagine doing, but this is just an example. So, okay, so update rules. So I want to emphasize that if you're trying to build update rules, so this relates to the question, input coefficient. What you could do is derive an update rule, which just makes the whole thing a neural network. So you could have the velocity at time n+1 is just a function at previous times where you enforce causality so that every point only takes in its neighbors when trying to figure out how it's update, but you simply let machine learning figure out what the form of G is. Like that's a perfectly reasonable update rule to derive. And this is an emulator, basically. This is a type of structures, under exploitation in many places, including, I know people at Livermore who are doing this, and I think it's a very interesting thing for many reasons. But so that's pure machine learning. So the second thing you could do, and this is what I was talking about with the Burger's equation example, is what you do is you take the velocity field and you put it into a neural network, which essentially does interpolation for you, and you then take that and put that into the normal equations of motion, but on a coarser grid to derive the update rule. So that's that. And this is sort of what the architecture is for what I'm about to show you. I mean, we basically stick the velocity field into a neural network. We compute, basically, we interpolate the nonlinear terms of the Navier-Stokes equations. We interpolate the fluxes basically onto the midpoints of the cells. That's the part that we use machine learning for. And then we just project onto divergence-free fields and time step, and we can insert the force. And so this is an example of inserting machine learning, but keeping the physics, the basic structure of Newton's laws are still there. And then the third thing you could imagine doing, which I think is also interesting, is you could take the velocity field, you could put it into your discretization that we always did, and then you could say, oh no, there's a mistake, and add a correction to it, and use that. And so these are three very different things. We call this one learned corrections. And so the point I want to make is there's no theory, there's no principle that says one of these is better than the other. And I think one of the challenges that actually exist, or one of the questions that exist in the field of people doing this right now, is to figure out in what situation which of these is better and how. And what I'm going to show you is kind of an effort to do this in one problem. So when you say better, though, you have to be careful. We have to be very careful about what we mean. So better means there are two different axes of the word better. One is accuracy, and the other is generalizability. So accuracy is what I've been talking about. In our case right now, reproducing DNS with coarser mesh with bigger time steps. Oh, I forgot to say actually that the way we've coded this thing, when we increase the mesh spacing, we assume a Coulomb condition with the time stepping, and so our time step is scaled with the space step, with the coarse space step. So we actually increase the time step in concordance with the step when we do what I'm about to show you, and also what I showed you before. So, but accuracy is one important thing. But the other important thing is generalizability. And of course, the reason that we all love the laws of physics is because the beauty of them is you can solve them for whatever problem you want, and they will work, right? They always work, basically. And so, and this is something which, if you train a pure machine learning model, this is gone, basically. I mean, generalizability is gone because you will only generalize if you've given it, the situations that it knows to learn the rules on. And so there's really a tension between these two things. And this is, I think, part of what's interesting here. And so what we did basically is, which is, as I'll show you, a 2D turbulence problem, is to adopt different types of generalization tests. So one generalization test is to basically consider a flow where the forcing is the same, it's a turbulent flow, but we have different random initial conditions. This is a rather popular test that people who train machine learning models do. I personally find it to be quite weak. And the reason is because if you're studying any problem that is complicated, then the solutions will be chaotic. And if they are chaotic, then we all know that there's a Lyapunov time beyond which essentially the dynamics becomes uncorrelated with the initial conditions anyway. And so randomizing the initial conditions is not so different than just being able to simulate forward in time. And so it's almost the same thing. So, I mean, this is a consistency check, but I'm not sure how impressive this is. So another thing you could do is change the forcing function. And then the sort of strongest test, and what I'm going to show you, is to actually take a model that was trained in one Reynolds number or a set of Reynolds numbers and use the scaling laws that we know from the theory of turbulence to change to different Reynolds numbers. So, okay, so here are the tests. So what we use and what I'm about to show you is Kolmogorov flow. So this is 2D turbulent flow that's forced with Kolmogorov forcing, which is just a canonical forcing function to drive flow. And the generalization tests that I will show you include both enlarging the domain and also turning off the forcing, which is like changing the forcing, and also changing the Reynolds number. So taking a model trained at one Reynolds number and going to another Reynolds number. So, okay, so in order to do the work I'm about to show you, we wrote a fully differentiable fluid solver in JAX. It's a finite volume code, and it basically makes it easy to do the sort of thing that I'm going to show you. And I mean, just as an example, so here's a GIF of a simulation of a turbulent flow, and you know, it's object oriented, and so you can just sort of roll out trajectories. Anyway, I'm not going to belabor this, but this is open sourced, and so people can play with it if they want. So here's the study. So what we did, what I'm going to show you is Kolmogorov flow with a Reynolds number of 1,000. We took ground truth trajectories from a high resolution simulation, was 20 feet squared, with each time step obeying the CFL condition with a scaling factor of 1/2. We take these ground trajectories down grid using truth. To train it, we took 30 trajectories with different random seeds. I rolled 40. Yep. Hello. Did something happen?
Yeah, it seems to be broken again. Maybe.
Oh, it's broken. Jeez,
Yeah.
I don't know what is wrong. I'm really sorry. You think it's my internet? I think this is possible.
Yeah.
Let me.
You can
hear me now?
Yeah, I can hear you. So you can restart this slide again, I guess.
Okay, yeah. I'm really sorry. I don't know I'm really sorry, everybody.
No worries.
This is the
Things can
downside
happen.
of. So okay, so what we did was we Kolmogorov flow with Reynolds number 1,000. We took ground truth trajectories from a high resolution simulation that was 2048 squared, where each time step obeyed the CFL condition with a factor of 1/2. We then downsampled this to coarser grids to be used as training data. To train it, we used 32 trajectories with different random seeds. We unrolled for 4,800 time steps, where the time step was modified to obey the CFL condition on the downsampled grid. And we then trained it with an L2 loss in which we unrolled over 32 time steps. So we didn't predict only the next time step. We found that when we did that the resulting scheme was unstable, but that by increasing the number of time steps in the loss, then that basically allowed us to find stable models that could be rolled out for very long. So model evaluation actually was the most expensive part of this process. We generated much longer trajectories, tens of thousands of steps, to make sure that the model was stable over long times. And so that's basically what we did. And now I'm going to sort of show you a couple of results. So this is a DNS of 2048 squared, and I've put in here, there's a box which shows you a turbulent structure which you can track as you go through different time steps, and this is plotting vorticity in 2 dimensions. So the direct simulation that's been downscaled to 64 squared is at the bottom, and what you see is that this initial structure still exists after 500 steps but dissipates after 1,000 steps, whereas in the learned solver, which is the middle row, it still tracks perfectly. I mean, actually, you see a slight discrepancy here, but remember the flow is also chaotic. So okay, so making this sort of into a picture, into a plot, this plots the vorticity correlation with respect to, as a function of time, with respect to the ground truth solver. This vertical dashed line is 3 Lyapunov times, and this is basically different. So this is the learned interpolation as the dashed line, which is 64 squared. And this is the 64 squared direct solve. And these are direct solves at different resolutions. So this is 248, this is 1024, and this is 512. And so what you see is that the 64 square learned interpolation is performing at a level which is basically in between 512 and 1024. So it's performing like a much higher resolution grid. It starts to peel off at around 3 Lyapunov times, which is basically the best you can expect to do. So now the reason why, and this is the same sort of comparison actually of accuracy, looking at spectra instead of looking at spectra at long times, instead of looking at just matching times. And spectra are useful because at very long times you want to make sure the scheme is getting the statistics right. And this basically just demonstrates that the learned scheme is getting the statistics right at the same level as the higher resolution schemes. So the interesting thing is that, so if you run this on a TPU v4, then we have 12.5 higher flops than the baseline CFD solver. Because of course we're running these neural networks to compute the interpolation schemes as we're going. And so the utilization fraction of the machine is higher. And so that means that despite having 150 times more operations, the ML-based solver is only 12 times slower than the baseline CFD solver. And so the grid spacing basically difference. I mean, actually, I didn't. So the grid spacing, actually, you could maintain accuracy by upscaling the grid by a factor of 10. And so what that means is that if you compute the speed up, the speed up is 10 cubed, right? It's 10 squared because of 2 dimensions, and there's another factor of 10 because of the time stepping. And then you have to divide by 12 because that's the cost of the ML solver. And so this is raw 80 times faster than the direct solve. And so this actually is I don't know, we think kind of interesting. And when we plot basically the sort of Pareto frontier, right, the runtime per time unit as a function of the time until the solution degrades, then basically what we see is that there's over a range of resolutions about a 90 times speed up. This actually is a slight underestimate we found later on. But anyway, but that's the result. And and then we took the same solver and we ran a bunch of generalization tests. So this is decaying turbulence, where you see that the thing still works. So this is the DNS, this is learned interpolation, and this is the direct solver, which loses the structures rather quickly. We did a test at higher Reynolds number. So this is what we did is we took a simulation at Reynolds number 4,000. So in 2 dimensions, the Kolmogorov scale scales like 1 over the square root of the Reynolds number. So the difference between Reynolds number 1,000 and 4,000, the Kolmogorov scale should go down by a factor of 1/2. So what we therefore did is took the model that we learned at Reynolds number 1,000, we cut the mesh spacing by 1/2, and we simply used the same model and found out that it worked also so this is 4,096, this is 128 squared with this model. So it's not quite as good as the other one. This is between 512 and 256, but it's still, right, allows substantial upscaling. This is a larger domain test, which works as well. And then finally, and then I'm almost out of time. I knew this was going to happen, so I will stop in 2 minutes. But then finally, what we did is we took all of the different types of models that I described at the beginning, and we compared them against each other. So we took learned interpolations, which I've just gone through carefully. We took the learned corrections, which you can sort of easily do as well. And then we took 2 types of ML models. These are just different architectures that people use. And we ran them across all of these benchmarks. And this is the result. This is a very messy slide, but there's a lot of compute in this slide, and I think there's one point. So each row is a different forcing. So this is the force turbulence that we use to train, larger domain, decaying, and more turbulent. And these are different metrics: point-wise accuracy, statistical accuracy, and stability. And these are the different models. So learned interpolation, learned correction, and these are the 2 pure machine learning models: a ResNet, and an EPD, just another architecture. Basically, what you see is that on the force turbulence, some of the machine learning models, especially with this EPD architecture, do perform at the same level as the trained models. That is, you can get pure ML models that have the same accuracy and stability as the models that we trained using the physics-based ways. But as soon as you start changing the task and making it harder, especially changing the forcing, larger domain, or increasing the Reynolds number, then the physics-based models outperform and the ML models don't generalize as well. And I think this is exactly what you would expect. And this is exactly the tension that I think that our community has to really try to understand, is that there are going to be some places where emulators are actually great. And but then there are going to be other places where actually including aspects of the physics in the solver is going to actually produce just better answers that generalize. And the figure out. So I'm going to tell you this is an outlook of the work I've just shown you, and then I'll show you one more summary slide on just general auto diff. So, I mean, with respect to this PDE solving, so we're still in the early days, but basically the scaling, if you think, so the runtime scales like n over k to the d plus 1. This is an explicit solver. So n is the number of mesh points. K is the effective coarse graining factor you can get away with, basically. And then there's a prefactor here, which the C physics comes from normal physics models, and this is the ML overhead. So right now in our hands, this ratio of CML to C physics is 12. If you assume that 10x decrease in resolution generalizes to 3D, then this number, then the speed up goes from 1,000 to 10,000, instead. And I mean, although this doesn't solve the intractable scaling problem I talked about at the beginning, every factor of 1,000, the joke is that every factor of 1,000 kind of helps. So this is actually, I think, kind of interesting, and there's a lot to be done. So the Google group actually is now working on a GCM. So I'm not going to talk about this, but just to sort of say it, which is, I think, another fun thing. And then finally, in the rest of my crazy number of topics, which you can see how crazy it is, I mean, we've actually been having a lot of fun recently with the visitor at Harvard designing rheology using Jack CFD, modifications of it to allow boundaries. And this is really fun. I don't have time to talk about it. And then I just want to end by, so this is a picture of my research group at Harvard, people who've contributed to this way of thinking. And these are people, I mean, I want to put up, these are the people who were really responsible for the work that I talked about here. And maybe there's time for a couple of questions. Thank you. And I apologize.
Thank you. Yeah, it seems to be broken again, but thank you so much, Michael. A wonderful talk. And very inspiring at the same time. So let's have a Q&A sessions. If you have any questions, please put that in the chat or unmute yourself. And okay, so the question from Amin, he asked about, could you please comment on steady state problems where there is no update rule to optimize using ML? How would you go about it?
Yeah, so I mean, can you give me an example?
Any time independent problem, like so all the examples you have shown is the time dependent problem.
Yeah.
Like
So I talked about time dependent update rules. I didn't talk about solving Laplace's equation or solving steady state heat transfer problems or things like that. So I think that's an interesting question. I mean, one sort of obvious comment. I mean, the answer is I don't really know, to be honest. But because we're trained to always answer questions even when we don't know. I mean, one obvious comment, of course, is that if we're talking about steady state heat transfer, then I mean, you could learn the operator from the time-dependent problem and then use the steady state version of it to try to learn the steady state problem. So that's certainly one thing that you could imagine doing. Otherwise, I mean, I think that you could imagine formulating steady state problems in this way if you wanted. There's a lot of room. I'm happy to talk about it in a minute. Sorry, I'm not sure I answered your question.
All right. Actually, Amin posted earlier another question. He asked about since your constant optimized form matches the Reno, the time integrator scheme, could that loosely mean that Reno is theoretically the lower limit for a fixed stencil?
I mean, I think that that's certainly what this suggests. I mean, we didn't try to match Reno. That's just what happened. So I think that this suggests that.
All right, sounds good. Next question is by Bruce Shelley. He asked about, could you please briefly again explain where is the automatic differentiation and the numerical solution used in your algorithm?
So the way that the automatic differentiation is using is, remember that we've defined the update rule so it depends on parameters which aren't known initially. They're the weights of the neural networks that are used for the interpolation functions. And so we then define a loss function, which is, to make the update rule so that it has the property that I describe, and you have to optimize the loss function with respect to the weights, basically. So in order to do that, you have to roll out the update rule in time, and you then have to take the derivative of the loss with respect to the weights, and that is where the automatic differentiation is used, is that the optimization is done with gradient descent, some optimizer that's a gradient-based optimizer. So I don't know if that makes sense, but that's...
Okay, sounds good. Okay, so next question is by Qui. What makes the ML model generalizable to different Reynolds number?
Right. So the generalization that I showed you was from 1,000 to 4,000, and there we simply used, the asymptotics of the turbulent cascade, right? You know, the Kolmogorov scale has a scaling with Reynolds number. And essentially what the scheme that I was describing does, we believe, is that it's essentially learning, as it were, the structure of the smallest eddy in the Kolmogorov scale and letting you represent it with less points. And in that spirit, since as the Reynolds number increases, then, you know, if you believe in the theory of turbulence, then it tells you that there's universality. And so you should be able to just rescale by, the, you know, 1 over the square root of Reynolds number in 2D, or, you know, what is it? It's the Reynolds number to the 3/4 power, or whatever it is in 3D, 1 over, anyway, whatever it is. And then you should be able to rescale and apply it to different Reynolds number. And you could actually use this as a training procedure, actually. There's lots of things you could do. We just checked that it worked from 1,000 to 4,000, which it did. I think that you could make a generalizable model of a Reynolds number. I think there's work that needs to be done there to sort of to do it definitively, but I think it could be done. And I think even in principle extrapolative. And I think what's actually interesting is, could you do this and let's do the largest DNS that's ever been done, and let's do it by generating training data up to some Reynolds number and then extrapolating to a larger one, demonstrating that it works, and then, you know, running a larger compute that you could do before. So I think there's room, basically.
Okay, so the next question is, I guess, related. Andre, he asked about how difficult would it be to apply the method to a higher Reynolds number, like 10 to the 6th or 10 to the 8th power.
Yeah. So I mean, I think in principle, there's nothing in principle that's wrong with this. The only thing that limited our Reynolds number was that Jack CFD right now runs on a single TPU or GPU, and so you'd have to write a distributed version of the code. But there's nothing about other than that, there's nothing that limits. I mean, you know, it's the same as always.
Right. Okay, so another question from Amin. Have you compared your method with a pure ML approach, but using a physics-informed loss function, such as add residual of the PD? Etc.
Yeah, so I should say, so this is a longer conversation. So I must admit, these physics-informed loss functions, I am confused by. Maybe that's the right way to say it. So I think that, you know, all of numerical analysis is about designing algorithms which minimize the residual of the PDE. And so, you know, if you're using the neural network to parameterize the nodes of the solution, and then you can certainly do that and use automatic differentiation to do that. But what I'm describing is, I think, quite different than that. So I think there's a longer conversation. I don't want to go too quickly, but I'm happy to discuss that. But it's I think it's different. I don't actually think that the two are comparable. I mean, I think for one thing, the parameter efficiency of the sorts of method that you are describing, I think, is much worse than the ones that I'm describing, and I don't think it's going to compare well because, but there's a longer conversation. So.
Yeah. All right. Another question is by Faye. What if the ground truth is noisy? Can you differentiate through it?
Yeah, I think that's a good question. I mean, you could, of course, create a loss function that's not L2. You could create some sort of a probabilistic loss function. There's a lot of room there. The part of the talk that I didn't give was about differentiating through solutions of Langevin equations that were describing materials assembly processes, and which is something that we do routinely. And so that, in that case, the ground truth is noisy. And what is, you know, create an ensemble average, we batch them, and then we ash. So there's room.
Okay, sounds good. Okay, another question is by Kian. Is there an opportunity to interpret the ML scheme to design adaptive numerical schemes?
There is, but I mean, I think that the Wino example is an interesting one with that. We didn't go into that in any depth, but I mean, it would be interesting to see if it would reproduce Wino, or if it would reproduce something which one could then go and derive. That would be cool. But we haven't gone down that road, but I think that it's interesting.
All right, sounds good. Question from me. I don't see any more questions in the chat room. So, you know, the example you showed, you know, the ML inference, the cost was 12 times slower than the, you know, the traditional one. And I guess you can optimize that, try to minimize that cost by, you know, exploring the structure of the neural net, etc. I guess you are doing
there's a lot of room there. We haven't worked on it at all. So this is the thing. This is the 12 is the number that came out of what we did, and we didn't try that at all. And as you know, there's been, you know, in general, there's been a lot of progress trying to create smaller models that have the same accuracy as larger models. So there's no reason not to be bullish about the ability to push that number down. I have no idea how much it can be pushed down. There's no reason not. I think there's no reason. There's every reason to think that can be improved.
Yeah. Okay, the next question is kind of related from Pranav. What are some approaches employed to select optimal hyperparameters? Yeah, that's, I guess, same answer to that.
Yeah, same answer there.
All right, the next question is by Kui. Does people work on something similar to in the context of high order finite elements where the operators are generally less bandied?
Yeah, I think that's a really interesting question. I don't know if anyone is. I think it's a really interesting direction.
Okay. All right. Is there
Okay.
any other question from audiences?
Okay, well, thanks
yeah,
everybody.
Kevin Corner, yeah. Please unmute.
So can you hear me?
Yeah.
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 Go
Okay.
ahead.
So first of all, really interesting talk. I've started working with some of these automatic differentiation methods recently, and I think that there's a lot of application. So one thing that you mentioned at the very beginning, I was just kind of wondering because I haven't quite had the time to sit down to this stuff, is using an automatic differentiation toolbox to basically get around using adjoint methods for sensitivity analysis.
Yeah.
What's the general trade-off there? So is it time, compute resources, memory? Is in your
There's certainly a memory trade. Certainly, the problem is if you're unrolling with automatic differentiation, then you're storing the entire computation, the partial derivatives on the entire computation graph, which if you're writing an adjoint, a general adjoint, you tend not to, you can sort of get around it basically by making it more efficient. So there is for sure a trade-off. But on the other hand, the two are quite synergistic. And at least for me, I haven't written adjoint codes for a while because of this. So.
Yeah, because there's always the question also of I was wondering what your thought on this was, because you could see two different approaches to using something like automatic differentiation. You can do sort of these large, massive problems where just writing derivatives by hand is completely unfeasible.
Yeah.
Or you can also take the interpretation, and these are not completely independent of just like using automatic differentiation as a rapid prototyping tool.
Yeah. Yeah. No, I agree with this. I think that and I unfortunately I'm going to say this, and I unfortunately have to run because I'm
Right. You have
just the thing, but I'm happy, Kevin, to talk about this more because I think this is interesting. The meta point I was trying to make was more the automatic, the rapid prototyping tool. I feel like if you don't have to rewrite the code every time you want to try something new, then it makes it easier to try new things. And when you figure out the right one, then we can always write efficient code however we want around it. But it's the trying new things that, especially when you're in this non-convex optimization, who knows what's going to work, what kind of scheme is going to be stable, what's going to be useful world. I just feel like that's the part that at least I find exciting. I know it's kind of boring in a way, like rapid prototyping as a reason to do science well, but I just feel like it's certainly a reason that the machine learning community has moved so quickly. And I just again wonder what our community could do with it if we thought about things this way.
Yeah.
Yeah. Thank you very much.
Okay.
All right.
Cool.
Thank you so much.
I appreciate all of your questions.
Yeah, let's thank our speaker. That's awesome. And thank you so much for
thanks everybody.
Thank you. Thank
I
you,
really
Mike.
appreciate it. Okay, bye.
Okay,
Ping
bye.
me if you have questions. Bye.
All right, bye.